And now that we have reviewed what we ended with yesterday, and that was the absolute value transformations, I would like to practice them, and we'll move on from there. We'll see what else we got going on after the compositions with absolute values. So it's pretty neat. It's a composition, it's a transformation, it's neat. I have a parabola for you over there. You don't need to know its equation, that's unimportant. What we are going to do is we are going to do the absolute value of that parabola. We're going to do f of the absolute value for that parabola. And then we're going to do a couple other neat things. We're going to apply a reflection to the absolute value of f of x. And then we're going to do the absolute value of f of the absolute value of x. Fun in a bun.
So you just put
But
absolute
we
values on the x and on the full equation?
kinda. We don't want to spoil the fun though. And I will have to scroll up and down, or I can just hold my notes. Maybe I'll just hold my notes so I don't have to scroll up and down for you guys, because it's hard for me to see the picture, obviously. You know, I don't have the benefit of looking right at the paper like you do. So for part A, what we were going to do was the absolute value of f of x. And what I did in each one of these is I put the original function on there as a dotted line, just like you saw in Desmos a moment ago. Cool. The absolute value of f of x. Now what that's going to do is it's going to take all of your positive y values and it's going to leave them alone, right? Because f of x means y values. However, any y value that was negative, that absolute value is going to make it positive. This is going to end up giving us a net reflection. So where our y values were already positive, absolutely nothing is going to happen. But where our y values were negative, we have forced them to become positive. So at x equals 0, it wanted to give us the y value -2. Now it's got to give us the y value +2. At x equals 1, it wanted to give us the y value -2. Now it's got to give us the y value +2. So we end up with a shape like this, which you just saw in Desmos, so that one's not too groundbreaking. In part B, we're supposed to be doing f of the absolute value of x. Okay, well, that means we're taking the absolute value of our x's. So where our x's were already positive, those absolute value bars do absolutely nothing because, well, x is already positive. So the side of our graph where x is positive, absolutely nothing is going to change. However, when we try to plug in negative numbers, for example, let's plug in x equals -1. Rather than being able to return the y value of 0 like it wants to, the very first thing we do when we plug in x equals -1 is take its absolute value, which gives us +1, which would return the y value that +1 gives us of -2. When we attempt to plug in -2, the absolute value bars will return a +2, which means the function gives us the same y value as when we plugged in x equals 2, so 0. So on and so forth. Let's see, what's the next one? 3. When we try to plug in -3, the absolute value bars change it to +3. So we get the y value that +3 would have given us, and that is 4. And the pattern continues, and we get an image like this. So the absolute value of x being plugged in where x used to be is going to create an even function. It is now symmetric around the y-axis. Neat, huh? I think so. But I'm a big old nerd. Let's see, part C. Part C puts a negative sign on the front of everything. If you think back to yesterday, that negative sign is outside, right? That's an outside change. Outside changes are always going to affect which one, x's or y's? Lots of people. The y values. That negative sign says, hey, take whatever graph you had and reflect it over the x-axis. So for part C, when it says negative absolute value of x, you're going to take part A, which is the absolute value of x, the blue curve, and you're going to reflect it over the y-axis. That means every one of its y values is now negative, every one of them. Well, right here, these y values were already negative, weren't they? So those don't have to do anything. They would have been the reflection of this. Let's see if I can draw this. We had that part, it's been reflected down. Let me get rid of those dotted lines.
Was it W, now it's an M?
Nah, yeah, it was a W, now it's an M, because the rest of it looks like this. Quick sketch. We just reflected part A upside down. Reflected it over the x-axis. I know I didn't do a really good job of hitting the points perfectly, but they were good enough. You get the idea. And then the interesting one, part D. The absolute value of f of the absolute value of x. What a weird thing to say. I have to like read it off of the paper. It's so hard to say. What is it going to do? It's going to combine the ideas of part A and part B. Well, part B, f of the absolute value of x. F of the absolute value of x produced this image. It's an even function, right? Now, if I were to slap some absolute value bars on all of its y values, the places where this graph in part B has positive y's are unchanged. But the places where the graph in part B has negative y values is going to do the same thing we did in A, reflect above the x-axis. So all my negative y values now become positive y values. So what points did we have? Negative 2, 0, and negative 3, 4. Negative 2, 0, and negative 3, 4. That part existed already. Now, instead of I'm going to do it in green. Instead of this shape down here, where did it go down to? Negative 1. Instead of this thing that we had down there, that M shape is going to reflect above the x-axis and come to negative 1, negative 2 comes to negative 1, positive 2. And 1, negative 2 comes to 1, positive 2. And my M shape comes up like that. Ta-da! The absolute value of f of the absolute value of x. Neat, huh? I think it's neat. I'll be real with you. I'd never seen this kind of transformation until I started teaching this class. It's one of the reasons why I like to teach upper level stuff. Every now and then I come across something that I hadn't done before, I hadn't thought of before. I like that a lot. So yesterday, other than these absolute value transformations and compositions, we did shift up, shift down, shift left, shift right, reflect over x, reflect over y. We saved the most fun things for last, and I say that kind of facetiously, stretches and shrinks. Vertical stretches, vertical shrinks, horizontal stretches, horizontal shrinks. And that is what's in this box down here. Stretches and shrinks of graphs. Yesterday, I kind of toyed with the idea with you guys that inside changes are opposite. X changes are opposite. And when I say opposite, I mean opposite effect. Not opposite number, opposite effect. And outside changes have the same effect of what we think they should have. That rule still holds true for horizontal and vertical dilations, also known as stretches and shrinks. Let's do the outside changes ones first, because I think that one's easier to think about. So do the one at the bottom. Y equals some constant times my f of x. So some constant stuck on the front. Outside numbers are y changes because f of x is my y values. So I'm saying take my y values and multiply by something. And y is a vertical thing, so if you took my y number, my height, and you put a 2 in front of it, you doubled my height, I'd be taller, wouldn't I? You could say that I vertically stretched. Well, that did exactly what I thought it would do. So once again, an outside change doing exactly what I think it should do. But if you put a 1/2 in front of my height, yeah, I'm going to be shorter, exactly half as tall. Again, doing exactly what you think that number would do. So if the number on the outside is bigger than 1, then that is going to be a vertical stretch. Now, once again, either our authors goofed this up or I typed it poorly. I think it's the authors. You can't say that it's a shrink if that constant is smaller than 1. That's poor. Why? Someone give me a number that's smaller than 1 that I can't put on the front of this thing. 0. Because if you put a 0 on the front, you don't have a function anymore. So I think that our authors were a little remiss. It's not that it can't be less than 1. I mean, it's not that it's less than 1. It's that it's between 0 and 1. So I'm going to strike through this, and I'm going to say 0 less than that constant less than 1. You see what I've done when I write that is I've also eliminated negative numbers. And that's important that you do that because negative signs are their own transformation. Remember, negative signs are reflections. So if I put a -2 on the front of a function, the negative sign is a reflection over the x-axis. The 2 is this, a stretch, because that number is bigger than 2. So I wrote this. These are y changes. They happen outside, and they have the same effect that we would expect. I'm setting you up for something when I do things like that. Same effect. Multiplying by 3 makes things taller. It literally multiplies the y values by 3. Now, inside stretches and shrinks. This is the one that really borks up people's brains. Because the inside changes, x changes, don't do what we want, and they have the opposite effect of what we think they should. Putting that 2 in front of the x does not stretch this thing left and right. It does the exact opposite of stretching it. It shrinks it. So when I say it's the opposite, I don't mean the opposite number. I mean the opposite effect. Putting a 2 in front of your x is actually going to cut the x values in half, shrinking it left and right, a horizontal shrink. But putting, say, a 1/3 in the front of your x, which you think, oh, well, I'm multiplying my x's by 1/3, they should be getting smaller, has the exact opposite effect. It's making them much larger. So that would be a stretch. Not dividing them by 3, multiplying them by 3. So the effect is the reciprocal effect. I put a 1/4 in front of my x, that's a horizontal stretch, factor 4. I put a 3 in front of my x, that's a horizontal shrink, factor 1/3. They have the reciprocal effect. And again, the author is a little bit remiss. You can't say if c is less than 1, you have to say if c is between 0 and 1. But notice that where the greater than or less than is in a different, not the greater than less than, the word stretch or shrink has been switched. See, shrink is on top now, shrink is on bottom there. They switched them. But this still has to be true between 0 and 1. And for this one, we have x changes. They're happening inside, and they have the opposite effect, not the opposite number. They actually have the reciprocal effect, but I like using the word opposite because I can use that term opposite when I talk about shifting left and right as well. Opposite effect. You guys comfortable with the reciprocal idea? Not the negative number, not the opposite number, it's the opposite effect. So reciprocal. Yeah? Basically, function notation lies to you. This function notation lies when you're talking about the x's. A description never lies. If I say horizontal shrink a factor 1/2, I mean squish that bad boy left and right. That's what I mean. But the function notation, horizontal shrink factor 1/2, would be f of 2x. It lies. Uses reciprocals. No panics, no screams of terror. Can I clear it?
Wait, how'd they put you on that quiz?
Oh, that's not talking about that on YouTube. All right, so we'll go ahead and clear this.
Did you realize that you were teaching it?
So, Hayo Voss is your buddy. You guys ever heard of Hayo Voss?
I think so.
Who was your Algebra 2 teacher?
Blue ball.
Blue Bomb. Who else had Blue Bomb? Did she say Hayo Voss? No?
We started at the end of the year.
Hayo Voss is your buddy. Hayo Voss is your key to transformations. It's kind of like PEMDAS, you know, where every letter stands for something. Hayo Voss is your transformation friend. And you notice that only the H and the V are capital. That's because H stands for horizontal transformations. And the V stands for vertical transformations, in case that wasn't going to be obvious enough. The second letter in both of those things tells you where these kinds of transformations occur. Horizontal transformations occur on the inside because they're, on the x. Whereas vertical transformations happen on the outside, on the y. And then the final letter describes the effect. Horizontal changes happen on the inside, and they have the opposite effect. Whereas vertical changes happen on the inside, and they have the same effect. And this means like the same effect that you would expect they have. This Heilvoss thing, it doesn't really apply to reflections, so just try not to break your brain making those work there. But it works for shifting and stretching and shrinking, which I think is pretty good. Heilvoss. My wife teaches Heilvoss to her Algebra 1 students at the middle school.
Oh, that's probably where I learned it from.
Was she your teacher?
I had Nell.
She did teach it to Miss Nell, and we're pretty sure that Miss Nell used it for 1 year, and then stopped after that. But Heilvoss, buddy of mine in Gainesville, fellow mathematician, he taught it to me when I told him I was going to be teaching Algebra 2. He's like, "Oh, Heilvoss," and I was like, "What'd you call me?" But then he taught me about it. I was like, "Oh, I love that." So now we can use our.
Weird insult is that?
I'm sorry.
You were like, what kind of weird insult is that?
Yeah. I mean, because I'd never heard of it. Because I told him, I was like, "Oh, my textbook starts with transformations," and he said, "Oh, okay, you mean Heilvoss?" And I said, "I have no idea what you're talking about." And he told me, and I was like, "Oh, you know what? I really like that, so I'll be using that from now on." And I've been using it for 5 years now. Now that we have refound our transformation skills, we can use them again, because you have done this in the past, to transform equations, write new equations. I have f of x equals the x to the third minus 16x. We're going to perform two different transformations. First one is a vertical stretch by a factor of 3. Okay. Vertical. Is that going to be changing the x's or the y's? Guys? Y's. Y changes. Inside or outside? Outside. Outside changes. Same effect or opposite effect? Same. The last thing that you have to do when you're doing transformations is remember the operation. See, stretching and shrinking is always a multiplication. Reflection is always a negative sign. Shifting is always addition, subtraction. So we've already said that it's outside and that's the same effect. So I'm going to change colors to black. I know I don't normally write in black, but we'll see. Here's f of x, and let me write what f of x is. Left the space in front of it on purpose. Because a vertical stretch of factor 3, we know it's going to be a multiplication. You guys have already told me it's on the outside, and you've already told me it's the same. So I expect a 3 out there, right on the front. 3 times f of x. But if you multiply the left side by 3, you have to multiply the right side by 3. And doing this is wrong, because I have not multiplied the entire right side by 3. You have to capture the entire side, so you use parentheses. And then you distribute your 3. And since we have changed this thing, it deserves its own name. G of x. 3x to the third minus 48x. And that graph will be 3 times taller than the other graph. Now the graph does go on to infinity, yes. But this one being taller, let's say it reaches infinity 3 times faster. If you could ever reach infinity. It gets there faster. Oh boy, phone call. So we're finished there. Part B, horizontal shrink, factor 1/2. Well, if the vertical stretch or shrink happen on the outside, then we know that this horizontal stretch or shrink is going to happen on the inside. So I'm in black, I'm just going to write f of, because I know the change is happening in there. Before I even care what that change is, this is how I teach Algebra 2 to do it. I go, look, everywhere you had an x, you are going to replace that x. So I strongly suggest just opening a set of parentheses everywhere there's an x and filling them afterwards. You go, okay, well, there was a set of parentheses. There was an x that had a third power on it. So there's a set of parentheses with a third power. Minus a 16. There used to be an x here, so now there's a set of parentheses. This is how I train the Algebra 2 students to do this. And I go, okay, now look, now we will worry about what goes inside those parentheses. We already know what's inside, but my question is, if it's inside, same or opposite? And lots of people would say opposite, and it doesn't mean opposite number. That doesn't mean I put a -1/2. It means I use the opposite effect, which is a reciprocal. So I'm not going to have a 1/2 x, I'm going to have a 2x reciprocal. And everywhere I had a set of parentheses, I drop that 2x. Right here, though, very easy for students to forget. This is not going to be 2x to the third. It's going to be 8x to the third, because that third power goes to both of those objects because they are separated by a multiplication. Our new function, g of x, will be 8x to the third minus 32x. And that graph will be twice as wide, excuse me, half as wide, my apologies, as the original one, half as wide. Cool beans? All right. Well, it's not new stuff. Now all we can do is combine skills. So combining transformations in order. We are going to deal with y equals x squared. And we're going to do these three transformations in the order that I have them. And afterwards, we're going to find the equation of our new graph. And it'll go through several name changes along the way, because every time you perform a transformation, you should change its name. A horizontal shift 2 units to the right. So I'm going to say g of x equals, so the first thing we're going to do is rename it to g of x. And this is going to be the function notation rule. G of x is going to be done by, see, shift 2 units to the right. Left and right is an x change. X changes are inside, and they are opposite. So if I'm going to the right, I'm not going to add 2 to my x, I'm going to subtract 2. Whoops. I forgot to write f. Come on, catch up. Please. There we go. F of. There we go. Much better. So the first thing we're going to do is replace all of my x's with an x minus 2. And we might as well do them in the order, like do it as they come across. So the first dot for part A.
Wait, why isn't it x squared minus 2?
Oh, well, this isn't the function itself. This is just the function notation rule. It's telling me what to do to my function. So that's not its answer. That's not the answer. That's telling me what to do. So I go, okay, g of x will be found by taking my function, replacing my x with an x minus 2, which looks like this. Where x was, I drop an x minus 2. So that is the new function, x minus 2 quantity squared. This is just the description of what you're going to do to the function. You're going to replace your x with x minus
squared minus 2.
No, it would be x minus 2 quantity squared, because if you do x squared minus 2, and that minus 2 is on the outside, that's shifting down 2. Has to be on the inside in order for it to be a horizontal change.
But if you put them all in parentheses, won't that work? X squared minus 2 in parentheses?
No, because x minus 2 quantity squared is not x squared minus 2 squared. It's, well, something like x squared minus 4x plus 4. So no, it would just be written like that. Think of it in vertex form. Right now, this one's vertex is 0, 0. If you shift that vertex to the left 2, it should be negative 2, 0. Excuse me, if you shift it to the right 2, it should be positive 2, 0, right? Well, positive 2 is what makes the inside equal 0 here, so we know that that's the correct answer for shifting to the right 2. A vertical stretch factor 3, we just did one of those, right? We just did it part A of the last question, so we know that it's going to be 3 on the front. So what I'm going to say is E, F, G, H. H is the next letter. I can alphabet. So H of x will be 3 on the front of my G of x. So H of x will be a 3 on the front of G of x, which legitimately just means slap a 3 in front of what you just had a second ago.
we have to boil this out?
No, no, no. We're going to leave it in vertex form. We like vertex form because it might as well be called transformation form. It shows us every transformation that's occurred. And the last one is a vertical translation, 5 units up. Shift up 5 units. HI is the next letter. So I of x will be found by taking the h that you just had and shifting up 5. Up and down is a y change, which is outside. Same effect, so plus 5. Just rewriting it. So it takes the result I had from above and then sticks a plus 5 on the back. There you go. So that function I of x is what you get when you take the parent quadratic and perform those 3 transformations to it. You will get 3 times the quantity x minus 2 squared plus 5. Its vertex is now at 2, 5, which we should expect because this one's vertex is at 0, 0. Shift it to the right 2 and then up 5 should be at 2, 5, and it is because it's what makes the inside equal 0, comma the number to the far right. Oh, and there's a 3 on the front, which means it's 3 times taller than the parent function. Cool? Okay. Part B. Apply the same transformations but in the opposite order and see what happens. Because guess what? It will not be the same equation. The order of transformations matters. So I went through the process again. Part B. We're going to do it in the exact opposite order. So we're going to say that our g of x now, first thing we're going to do is shift it up. So our g of x will be our f of x, which is the parent function, x squared, and we're going to shift it up 5. We're going to see what we get. We get x squared and plus 5. Vertex is now at 0, 5. The one in the middle is still going to be the one in the middle. Now we perform the vertical stretch factor 3, which means we take our g of x and we slap a 3 on the outside of it. But didn't I technically multiply the entire left side of the equation by 3, g of x? I mean, I'm pretty sure that's obvious. Yeah, I took everything that g of x was and I multiplied it by 3, which means I have to take everything that g of x was on this side and I have to multiply it by 3. Everything. So when you distribute that 5, you get, or excuse me, that 3, you get 3x squared plus 15. Wow, its vertex is now at 0, 15. And lastly, now shift it to the right 2 units. Which means take what h was and replace every x with x minus 2. So where I had an x, I drop a set of parentheses, and I plug in x minus 2. This one's vertex is at 2, 15. It is 3 times taller than the parent, but its vertex is at 2, 15. Performed in the opposite order, its vertex was at 2, 5, and 3 times the height of the parent function. So what I'd like you to do, and that's what we're going to call it for today, what I'd like you to do is think about what was different. So let's talk about it. The vertex of the first set was at 2, 5. When done in reverse order, the vertex was at 2, 15. Which one changed? The x or the y? The y. So the difference between these two vertices is the y. In fact, if you were to graph these two things, they're the exact same graph. One is just shifted 10 units higher than the other one. Notice that the vertex, the x value of the vertex, is exactly the same. So why was that unaffected? Why did that stay the same, but the, did I say the y? No, I can't remember what I said. The x value of the vertex did not change. It still landed at 2. But why did the y value of the vertex land at 2 different spots? Yeah, what do you think?
Because when you went from g of x to h of x, instead of just multiplying the one thing,
Mhm.
minus 2, you're multiplying it by x squared plus 5.
Yeah, so I had to distribute the 3 across the entire thing, right?
Yeah. And it's
Well,
bigger.
what we're getting at here is that order of transformations matters. You guys have heard of order of operations. Did you know there's an order of transformations? There is. Now, if I dictate the order in which you have to do transformations, like I did on this one, you do exactly what you're told. But if you were to describe the transformations that have happened to an equation, there is an order in which you need to describe them. So I'm just going to sneak peek you onto tomorrow's stuff. I just want you thinking about this. This is a sneak peek. How do you spell peak? Is it with an E? When you're peeking at something? Yeah. EA is like the peak of a mountain, right? Sneak peek. If I wrote this, and I said describe all the transformations that have occurred to the parent function, there is a correct order for you to describe those in. And I would just challenge you tonight to try to think about what it is. And tomorrow, if you would please remind me of what that equation is that I just wrote so that we can do that together. Just think on it.